So let's jump to our second topic, and this is the service model of the internet. We've just seen that the internet is basically made up by these individually operated networks, which are we call the autonomous systems. The name actually just tries to just stress that these are autonomously operated networks, which in and on themselves might not even need to run IP routing internally. What's very important is that on their border routers, they use IP to exchange traffic to the rest of the internet and use IP routing protocols, like in this case the internet EGP called BGP, to actually exchange routing information with the rest of the network. And as long as that's true, an autonomous system can be connected to the rest of the internet and gains access to the rest of the to the hosts and routers that are also connected to the internet. We are actually asking two questions. When it is the case that two autonomous systems create a physical connectivity between two or more border routers in the internet, so when it is the case that two ASs establish a direct connection between one another, and the other question that we ask is when it is the case that a particular AS, an intermediary AS, say in this example AS2, allows traffic from two different ASs, between two different ASs, to flow through its own network, and when it is the case that such traffic is blocked. So these two particular questions, we are going to use the internet service model to answer this simple question, and by the end of this of the next the next seminar, we're going to just have a high-level mental view of this service model and the type of large-scale structure of the internet that arises by this service model. So again, the internet is shaped by two very important factors. One is which is the ASs that maintain physical connectivity between their networks. So when it is the case that two ASs decide to connect their networks through particular border routers. So this is one important factor that shapes the large-scale structure of the internet. The second important factor is how do we actually route traffic on top of the topology, the AS level topology that arises as the collection of these physical connections between ASs. So these are the two questions, the topology and the routing on top of this topology, that is going to be the most important question that we ask in this seminar and the next. What we are going to see is that it is the business and political interests and the reliability and security issues that govern the way ASs connect their networks with physical links and route traffic on top of these physical connections. So it's very important. It is not technical considerations like path lengths or latency or bandwidth or things like that shape internet routes and the internet topology. It is much more about business and political interest. So it's much less of a technical issue than an actual political and business issue. And this is the collective name of what we mean by policy routing, where the packet forwarding is not shaped by technical considerations, but rather it is shaped by policy considerations, business, political, security, reliability, and whatever issues. So again, we want to stress that despite of the fact that in the intra-domain routing, so whenever we talk about RIP and OSPF and we talk about routing inside a single AS, most of the time what we have is full visibility into the internet, into the AS level topology of the organizational unit and the shortest path routing. But between autonomous systems, so in inter-domain routing, we don't even know the topology of the internet at that scale, and since we don't know the topology, we cannot have shortest path routing, and in fact internet traffic does not follow shortest passes. This is contrary to common belief. What we have is on internet passes is usually much longer than the absolute physically shortest possible path between two ASs. This is what is usually described by this measure, which is called path inflation, in this context. Again, we want to stress that the service model will describe two things in this scenario. One is the number of and the types of physical connectivity that can exist between two ASs, and the second is the routing strategies or the different types of intra-AS routes that can arise on top of this topology. The service model is basically the collection of all the concepts and definitions and the models that we will use to reason about the internet topology and the routing, the types of routes that arise on top of this topology. In order to actually understand what's going on in the background, we're going to need a couple of definitions. So far, we haven't discussed interdomain routing in too much detail, but to be able to get a good understanding of what follows, we at least need to build a very basic understanding of how and by which measures routing between autonomous systems actually occur. Okay. The first step is the following. Suppose that we have a destination autonomous system, and this particular autonomous system somehow acquired this IP prefix. This particular prefix in this case is one of the prefixes of the YouTube server. So this is the prefixes that prefix that Google uses to number its the YouTube servers that it operates in one of its data centers. What happens? We can imagine that in this particular destination there are lots of actual hosts which are numbered from this IP prefix, and what this destination AS wants is that it wants to inform the rest of the networks, the rest of the autonomous systems in the internet. Then whenever there is a packet whose destination address falls or belongs to this IP prefix, then it is the particular destination AS that the rest of the internet must use to reach these IP hosts. So this destination AS actually promises to the rest of the internet that if anyone routes any packet that have destination address in this prefix to its autonomous system border router, then from there it will make sure that the corresponding traffic will flow to the particular host that uses that particular IP address. Now, how this actually occurs? How this actually occurs is that this destination AS actually informs the rest of the autonomous systems about the whereabouts of this prefix. So it generates a so-called announcement. It announces to the neighboring autonomous systems that, dear autonomous system 1, if you want any packet that you want to route into this prefix, then use my autonomous system as your destination, because I provide the connectivity to this prefix. The same announcement is actually generated to AS3. Now we immediately see that AS3 and AS1 immediately gain a path to this destination AS, and again from this AS to the particular hosts that actually contain or possessed or are numbered with these IP addresses. Now, if AS3 actually decides that it is willing to route the traffic of AS2 through its network to the destination AS, then it re-announces the previous announcements to AS2. Dear AS2, if you want to reach the destination AS and any hosts within this IP prefix, then use my network and use these two AS hop paths to reach to this destination. Now, the collection of all these announcements that travel between different neighboring ASs is what we call the routing state of the internet, and in a particular remote router, it actually learns the reachability of this IP prefix from the announcements it receives from the neighboring ASs. So in this case, it now receives an announcement from AS2 about, say, this path, and from AS1 through this path, and in this particular case, it chooses the upper path to reach the destination AS. So again, interdomain routing is basically boils down to a distributed mechanism when neighboring ASs, in particular the border routers of neighboring ASs, exchange BGP announcements with one another, which announce reachability informations to particular IP prefixes in the internet.